So, um, imagine you're sitting at your desk, right? You are about to present in like an incredibly important video meeting.
Oh, yeah, the worst possible time for things to go wrong.
Exactly. Your boss is on the call, maybe a huge client is waiting for your pitch. You unmute yourself, you start to speak, and, well, the dreaded freeze happens.
Right, your video just stutters into this pixelated mess.
Yeah, and your audio sounds like you're speaking through, I don't know, a desk fan from 1995. You glance over at the door to the hallway, and you know exactly what's happening.
Someone is using all the internet.
Exactly. In the next room, someone is downloading a massive 100-gigabyte game update on their console. And downstairs, someone else is streaming a 4K movie.
It's the universally dreaded battle for bandwidth, you know? In most households, or even like small offices, it's a zero-sum game.
Right.
If the console takes the bandwidth, well, your video call just starves.
It's basically a traffic jam inside your router. And today's deep dive is all about solving this exact problem. But, I mean, we aren't talking about just buying a slightly more expensive router from the electronics store.
No, not at all.
We are talking about radically rethinking how our networks are built, like, from the ground up. The mission today is to explore this fascinating architectural shift. We're moving away from massive, distant cloud servers and bringing the brain directly into your building.
Which honestly represents a profound reversal in how the tech industry handles data. I mean, for the last 10 to 15 years, the default answer for any computational problem has been send it to the cloud.
Right, just put it in a data center somewhere.
Exactly. But the sources we're examining today indicate that model is physically and economically buckling. We are looking at a paradigm that flips the cloud model entirely on its head.
So the core architecture we are unpacking today is based on having one powerful central workstation. Think of it as a highly capable smart gateway or like a local home server.
Yeah.
And that one workstation manages multiple user nodes. And by nodes, we mean your computers, your smart home devices, IoT sensors, security cameras.
Or if you're in a school, 30 different student tablets in a single classroom.
Right, exactly. We're going to explore how this one-to-many setup allows for incredible resource management, distributed compute power, and, like, airtight privacy.
And I just have to say, the stack of sources driving this discussion today is incredibly rich. We're pulling from academic research detailing the cloudless home ecosystem and examining breakthroughs in AI-driven Wi-Fi systems by MediaTek.
Oh, and we're diving into the DOT anomaly detection system for IoT security, right?
Yeah, plus enterprise-level surveys on machine learning at the network edge. We're also drawing on insights regarding intent-based networking paradigms from experts like Ashish and institutions like Networkers Home.
So it's basically a comprehensive blueprint of the whole edge compute revolution.
It really is.
To help you visualize this, think of the old network model, the cloud-dependent model, as a massive centralized post office located like 3 carats away from you.
Okay, I like this analogy.
Right, so every time you want to send a quick note to your roommate in the next bedroom, you have to write it, mail it to that post office 3 towns away, wait for them to sort it, and then wait for them to send it all the way back to your house.
Which is wildly inefficient.
Exactly. It is attempting to micromanage your household's mail from miles away.
Highly inefficient, prone to massive delays, and honestly a privacy nightmare. I mean, think about a third-party opening and reading every single postcard just to route it back to your own living room.
Yeah, that's creepy. So this new architecture we're diving into is like firing that distant post office and hiring a brilliant, incredibly fast mailroom manager to sit right inside your front door.
Right. They instantly sort and route packages exactly where they need to go.
Exactly. Locally, without anything ever leaving the building.
No.
But to understand why we desperately need this local mailroom manager, we first have to look at why the centralized cloud is failing us.
And the sources outline a pretty harsh reality here, starting with the sheer volume of data being generated today.
Yeah, I saw the number. We are looking at an estimated 25 billion IoT devices currently active. 25 billion.
Let's put that 25 billion into perspective because we aren't just talking about laptops and phones anymore.
Right.
We're talking about smart thermostats, factory floor vibration sensors, connected vehicles, security cameras. I mean, if every single one of those 25 billion devices attempts to send its raw, unfiltered data up to a centralized cloud server to be processed,
You run into the unforgiving laws of physics.
exactly. You run out of bandwidth and you run into severe latency limitations.
Even with fiber optics, right?
Yeah, I mean, even data traveling at the speed of light through fiber optic cables takes time. It has to travel from your house in Chicago to a data center in Virginia, get processed by a server, and travel back.
And when you multiply that tiny delay by billions of simultaneous requests,
The core infrastructure of the internet begins to act like a highway at rush hour, with all the lanes converging into a single toll booth. The physics of it simply do not scale.
and it's not just a theoretical physics problem, is it?
Yeah.
It's a massive bleeding economic burden for the companies running these systems.
Oh, absolutely.
The research includes a study from Floyer that perfectly illustrates this at an industrial scale. They analyzed the data management and processing costs for a remote wind farm.
And a wind farm is like the perfect stress test for the cloud model. A modern wind turbine isn't just a propeller on a stick anymore.
Right, it's a super complex machine.
Yeah, it's generating thousands of data points a second. You have sensors monitoring blade pitch, gearbox temperature, generator vibration, wind speed, wind direction, you name it.
On top of that, the farm has physical security, right? Like video surveillance cameras monitoring the perimeter and access sensors on the gates.
Exactly. So Floyer calculated the raw cost of running this entire operation through the cloud, streaming all that constant telemetry, all those high-definition video feeds, up to a remote server for processing.
And the number is wild. The annual cost for a cloud-only system was calculated at $80,531.
Yeah, mostly in data transmission fees and cloud compute time.
But then they modeled a combined edge cloud system. In this model, they put a local server, like our workstation, right there at the wind farm.
Right, so the processing happens locally.
Exactly. The video feeds are analyzed on-site by AI, and the turbine sensors are monitored locally. The only thing sent to the cloud is a tiny text summary, like an alert saying Turbine 4 requires maintenance.
Instead of streaming hours of healthy turbine data, which is just a waste.
Yeah. And when they did this, the cost plummeted to $28,927.
Which translates to a 36% reduction in total operating costs.
That's a massive savings.
It is, but the truly staggering metric they found was the reduction in data transfer. By processing the raw data at the edge of the network, right where it was generated, they reduced the volume of data sent over the network by 96%.
They eliminated 96% of the traffic.
Yes. It is a massive validation of the edge computing model. When you scale that 96% reduction across thousands of global industries, you begin to see why relying solely on the cloud is economically unsustainable for the Internet of Things.
Wow. Okay, so money and bandwidth are huge drivers, obviously. But there is a third pillar here, and it is arguably the most visceral for you, the average person: privacy.
Oh, privacy is huge.
Because when your data leaves your local network and travels to a cloud server, you fundamentally lose sovereignty over it.
Yeah, and the research specifically highlights the UFI security camera incident to drive this point home. It serves as like a textbook example of the hidden dangers of third-party cloud processing.
Oh man, I remember when this story broke. It was a massive wake-up call because UDFI marketed their security cameras specifically on the promise of local storage and strict privacy.
Right, the pitch was basically, buy our system, the video stays on a box in your house, no cloud subscriptions required.
But security researchers dug into the network traffic and found a glaring issue.
They found that certain convenience features actually relied on the cloud. So, for example, if you wanted a push notification on your phone with a little thumbnail image of the person at your front door, the system couldn't generate that and send it locally.
Wait, so what was it doing?
It was taking that image, uploading it to an AWS cloud server owned by UTFI, and pushing it to your phone from there.
And the really concerning part was how those images were stored, right? Researchers discovered that if you knew the right URL structure, you could potentially access these feeds or images via a standard web browser.
Yeah, without any authentication. It perfectly illustrates the honeypot problem of cloud architecture.
The honeypot problem.
Yeah, if your device relies on a remote server to function, you are entirely at the mercy of that company's security practices, their encryption standards, and their internal privacy policies.
Right.
Even if a company has the best intentions, a centralized cloud server holding millions of users' private data is an incredibly lucrative target for hackers. A breach at the cloud level exposes everyone simultaneously.
So the solution to the bandwidth bottleneck, the crippling cloud costs, and the privacy nightmares is edge computing.
Exactly.
Moving the intelligence away from the distant data center and putting it on the edge of the network, physically close to the sensors. Put a smart AI chip in my home router. let it manage my bandwidth locally, process my security cameras securely, keep my data safe. Sounds like a utopia.
It does,
Now,
but
the sources point out a massive economic hurdle stopping this from happening tomorrow, don't they?
yeah, the hurdle is the brutal reality of telecom hardware economics. Think about the router sitting in your living room right now.
The black box collecting dust in the corner.
That's the one your internet service provider, your ISP, gave you when you signed up. That home gateway market is defined by incredibly low margins and massive volume.
Oh, right. ISPs basically give you those boxes for free or for a negligible rental fee
Mm.
just to hook you into their monthly subscription plan. They want the absolute cheapest piece of plastic and silicon that will turn the internet on.
Exactly. So integrating advanced AI hardware into those boxes, like a neural processing unit or enough high-speed RAM to run a local large language model, would substantially increase the manufacturing cost per unit.
Yeah, I can see that.
The ISPs are looking at this architecture and saying, why should we absorb a $50 or $100 hardware cost increase per customer if we can't immediately monetize the benefit?
Wait, hold on. If putting a mini supercomputer in every home or classroom router is just too expensive for the telecom giants to swallow, how does this edge revolution actually become a reality for us? Are we just stuck waiting around? Because one of the sources actually described the current state of commercial AI models in networking as resembling medieval alchemy. Are we stuck in the dark ages because of router profit margins?
If we wait for ISPs to generously hand out enterprise-grade AI hardware out of the goodness of their hearts, yes, we will be waiting a very long time.
Right.
The sources point out that widespread commercial adoption by ISPs would require entirely new and likely unpopular business models,
Unpopular how? Like what?
like quality of experience or QoE premium tariffs. Imagine your ISP telling you, we can guarantee your video call won't freeze when your kid downloads a game, but it requires our new AI smart router, which adds $20 a month to your bill.
Oh, I definitely do not want to pay a premium toll to my ISP just so my network routes traffic properly. I already pay enough.
Exactly, and you shouldn't have to. The most exciting development outlined in the research isn't happening at the ISP level at all. It is happening at the user level, driven by open source software and local user-owned hardware.
So we can do it ourselves?
You don't need the ISP to provide the brain. You can architect the mailroom manager yourself.
Which brings us to the actual mechanics of how this works.
Mhm.
The research paper on the cloudless home ecosystem gives us a literal step-by-step blueprint for building this central intelligence.
It's a fantastic paper.
It outlines the one workstation, multiple nodes architecture. Let's define the physical setup first.
Sure. So the workstation is the local server. It's the brain. In a residential setting, this could be a dedicated mini PC, a high-end Raspberry Pi setup, or even an old repurposed desktop computer shoved in a closet.
Okay, and in a bigger setting,
In a school or office, it might be a small rack-mounted server.
and the nodes are the workers, right?
Exactly. The nodes are the endpoints. These are the physical switch boxes controlling your lights and HVAC, the front-end applications running on your smartphone, your security cameras, or the environmental sensors in a server room.
So the nodes are the hands and eyes. They execute actions and collect data, and the workstation does all the heavy computational thinking.
That's the setup, yeah.
But if you funnel all the thinking into one machine, doesn't it just get overwhelmed? I mean, my computer freezes if I have too many browser tabs open.
Right. So the researchers solved this by using a microservice architecture. They used separate concurrent microservices based on Flask, which is a popular web framework for Python.
I love the elegance of this. They didn't just write one giant monolithic software program trying to juggle everything at once.
Oh, a monolithic application would be a disaster here. I mean, if you have one program handling video feeds, voice commands, and file storage, what happens when it tries to process a complex AI voice request?
It freezes.
The entire program pauses to think. Your video feed freezes, your light switch stops responding.
The dreaded thread blocking.
Precisely. By using Flask microservices, they divide the labor into independent processes. The workstation is running several isolated servers simultaneously, each dedicated to a single task.
The sources list 4 specific servers they built into this workstation, and it really shows the scope of what this single machine is handling.
Yeah, let's go through them.
Okay, so you have an automation server, which runs the logic of what devices should turn on and when. You have a NAS server, network-attached storage, for processing and securely storing local files.
Right.
Then you have an AI voice assistant server, and finally you have a WebSocket server specifically dedicated to handling real-time security camera feeds.
And the distinction between the AI server and that WebSocket server is crucial. WebSockets provide a persistent, full duplex communication channel.
What does that mean in plain English?
Well, unlike standard HTTP requests where the camera has to constantly ask, "Are you there? Can I send a frame?"
Hmm.
A WebSocket keeps the line open continuously.
Oh, I see.
Because it's running as an independent microservice on its own port, the heavy computational lifting of the AI voice assistant server doesn't introduce a single millisecond of latency to the security camera feed. They operate in parallel.
Okay, so the workstation is cleanly divided, the traffic is flowing, but where does the actual intelligence live? How does this box actually think?
That's the fun part.
The source details that this cloudless system uses the Llama 3.1 8B model running locally via a tool called a Llama. For the listener who might not be deep into the architecture of large language models, what does 8B actually mean, and why is this specific model the linchpin of the whole operation?
So 8B refers to 8 billion parameters. In a neural network, parameters are essentially the mathematical weights and biases that determine how the model makes decisions.
Like synapses in a brain.
Yeah, you can loosely think of them as the artificial synapses of the AI's brain. The parameter count generally dictates the model's capability. There are massive models deployed in data centers right now, like the Llama 3.17 Euro B, which
Yeah.
has 70 billion parameters, or even models pushing past 100 billion.
But wait, if 70 billion is smarter, why use the 8 billion model? Don't we want the smartest brain possible?
We do, but we are limited by RAM and computational overhead. When you run an AI model, those parameters have to be loaded into the computer's active memory.
Oh.
A 70 billion parameter model requires massive amounts of high-speed GPU memory. We are talking about server racks that consume incredible amounts of electricity, generate heat that sounds like a jet engine taking off, and cost tens of thousands of dollars. You can't put that in a hallway closet.
Yeah, definitely not. So the 8D model is the compromise.
Exactly. The researchers identified the 8B model as the current sweet spot for an edge workstation. Through processes like quantization, which essentially compresses the mathematical precision of the parameters so they take up less memory space, you can fit an 8B model onto the RAM of a standard consumer mini PC.
Oh, that's clever.
It strikes the perfect balance. It possesses enough complex reasoning ability to understand nuanced natural language commands and generate structured code, but it is small enough to run quickly without massive hardware.
And because it runs locally using a Llama,
Yeah.
every single voice command you speak stays in your house, right?
Completely local. It never pings OpenAI. It never pings Google.
And here is the part of the research that absolutely fascinated me. How does this Llama AI actually talk to the nodes? If I walk into a room and say, turn off the lights, how does the physical electrical circuit actually break?
Right. How do you get from a voice to a physical action?
The research details a process of intent recognition and JSON formatting.
This is where we see a massive leap forward from early smart home technology. I mean, think back 5 years ago. If you wanted to turn on a fan, you had to memorize rigid robotic syntax. You had to say, execute command, fan speed 3 in zone A.
You had to speak to it like a computer.
Exactly. The system was just matching keywords. But this cloudless architecture uses distributed prompt engineering. The Llama model isn't acting as a conversational chatbot. It is explicitly instructed to act as an intent recognizer.
Meaning I can speak to it like a normal human. Like if I walk into my bedroom and say, oh, it feels really hot in here, the AI actually understands what I want.
It understands the underlying intent is to cool the room down. However, the automation server, the microservice that actually sends the electrical signal to the switchbox node, does not understand conversational English.
It's just looking for a command.
Right. It doesn't know what, ugh, it feels hot means. It requires stripped, structured, machine-readable commands to function.
This is where JSON comes in, right?
Yeah.
JavaScript object notation.
Yes. The AI is constrained by a strict syntax requirement. It must translate your chaotic human intent into a perfectly structured JSON data package. A JSON file uses a system of key-value pairs.
Okay, so how does that look in practice?
So the Llama model takes, it feels hot in John's bedroom, parses the intent, and generates a JSON package.
It essentially fills out a digital form.
Exactly. It creates a package that explicitly lists device type, fan, target room, John's bedroom, and action, set speed to 3.
And then it hands that perfectly formatted JSON package over to the automation server, which reads the data and executes it flawlessly on the specific node.
It bridges the gap between the ambiguity of human speech and the absolute rigidity of machine execution, and it does the translation locally in milliseconds.
I was trying to conceptualize this microservice architecture, and it reminds me of a high-end restaurant kitchen.
Okay, lay it on me. Let's hear the analogy.
So the local server, our workstation, is the executive chef. Now, instead of one frantic person trying to cook every dish, wash the dishes, and take the order simultaneously, the executive chef manages specialized sous chefs.
Which are the microservices?
Right. You have one sous chef strictly handling the pantry and storage, which is the NAS.
Yeah.
Another is watching the dining room to make sure no one steals the silverware, that's the camera feeds. And another taking the complicated custom orders from the guests, the AI voice server.
That maps perfectly onto the Flask architecture.
So when a waiter runs into the kitchen with a messy scribbled order from a customer, like, I want this steak, but like, not too pink, and maybe swap the potatoes for something green because I'm on a diet.
Which is the natural language voice command.
Exactly. The AI sous chef reads it, figures out the actual intent, and rewrites it into a perfectly formatted, standardized order ticket, the JSON. They pass that clean ticket to the line cooks, the physical nodes.
And the line cooks don't need to understand the customer's diet. They just follow the precise instructions on the ticket and fire the steak.
Precisely. And because it's a closed kitchen, nobody outside the restaurant ever knows what you ordered or how you modified it.
It's totally private. But that closed system introduces a critical challenge: remote access.
Right. If we cut out the cloud entirely, how do I actually use this? What happens when I'm at the grocery store and I want to check my local security cameras or turn on the porch light before I get home?
Yeah, that's the big question.
If my phone is on a cellular network, doesn't it have to route through a cloud server to find my house?
Traditionally, yes. And this is where the researchers made a brilliant architectural decision. They designed the system to have secure remote access without relying on centralized cloud relays by utilizing Tailscale VPN and the WireGuard encryption protocol.
Let's unpack Tailscale, because the text heavily emphasizes it as a superior alternative to traditional cloud-based virtual private networks. Why is it better?
Well, if you use a traditional cloud VPN to check your cameras, your phone essentially talks to a massive centralized server, maybe located in Ohio.
Okay.
That server in Ohio then reaches out, authenticates with your home router, pulls the video feed, and relays it back to your phone.
So it adds a massive middleman to the transaction.
A middleman that introduces significant latency. The data has to travel hundreds of miles out of its way. The research notes traditional cloud VPNs operate with a latency of around 100 to 300 milliseconds.
Yeah, that definitely feels laggy when you're trying to view a live feed.
It does. And furthermore, a third-party company is handling all your encrypted traffic.
So how does Tailscale bypass the middleman?
Tailscale creates a peer-to-peer mesh network. It uses WireGuard, which is a state-of-the-art, incredibly lightweight cryptographic protocol. Instead of routing traffic through Ohio, Tailscale essentially helps your phone and your home workstation find each other on the internet and then creates a direct encrypted tunnel straight between them.
Oh, wow. They talk directly to each other. So what does that do to the latency?
The drop is dramatic. By eliminating the centralized server relay, the peer-to-peer latency with Tailscale drops to between 10 and 50 milliseconds.
That's functionally instantaneous to human perception.
It really is. You get the convenience of cloud-like remote access, but with the security, privacy, and speed of a completely local peer-to-peer network.
So we have this incredibly efficient local executive chef. We've fired the distant post office. We've secured the kitchen doors with peer-to-peer encryption. But here is the next logical hurdle in this architecture. If this single workstation is doing all this complex AI intent recognition, managing the storage, and streaming the video feeds, I mean, how does it physically handle that massive computational load without buckling? Does the workstation just melt down under the pressure?
It absolutely would if it were forced to do it all alone. But it doesn't.
It doesn't.
No, the architecture recruits the line cooks, the nodes, to help do the math. And this brings us to a massive shift in how networks operate, distributing the compute and collaboration across nodes.
Okay, so we're moving from just managing a local network to actually creating a distributed supercomputer.
Precisely. Instead of the central workstation hoarding 100% of the AI processing tasks, the architecture actively fragments and shares the compute power across multiple devices. This paradigm is known as distributed inference.
Let's break down a specific framework for this mentioned in the text.
Yeah.
Vertically distributed inference, specifically looking at the MODI platform. MODI stands for Mobile Deep Inference, right?
Okay.
How does MODI decide who does the heavy lifting?
MODI treats the entire end-to-edge to cloud architecture as a living, dynamic environment. Let's imagine you have a smart security camera, an end node.
Okay, got the camera.
The camera captures an image of something moving and needs to run an object detection AI to see if it's an intruder or just a stray dog. Modi doesn't just blindly send the image to the workstation. It dynamically assesses the current state of the network in real time.
Like checking the weather.
Exactly.
Yeah.
What is the Wi-Fi bandwidth looking like at this exact millisecond? What is the battery level or power state of the camera itself?
So it takes the pulse of the entire system before acting.
Right. And based on that telemetry, it makes a calculated decision. If the Wi-Fi network is heavily congested because someone is downloading that 100-gigabyte game update, but the camera has plenty of power, Modi will dynamically choose to run a highly compressed, smaller version of the AI model directly on the resource-constrained end node, the camera itself.
It forces the node to do the math to save the network bandwidth. That's so smart. But what if the camera is running low on battery? Or the small AI model isn't confident in what it's seeing and needs a really high accuracy reading?
Then Modi offloads the task. It transmits the image data up the chain to the more powerful edge server, our workstation, to run the uncompressed, highly accurate, resource-heavy model. It is constantly shifting the computational workload vertically up and down the chain to optimize overall system performance and latency.
Wow. And there's another concept nested in this that completely blew my mind. Early exit of inference, or EOI, utilizing distributed deep neural networks, or DDNNs.
Yeah, that's a mouthful.
It sounds incredibly dense, but the mechanics of it are brilliant. The neural network isn't just sitting on one machine. It is physically mapped across the nodes, the workstation, and potentially the cloud.
To visualize a DDNN, you have to understand how a deep neural network processes data. It works in sequential layers.
Like an onion.
Kind of, yeah. Data enters layer 1, basic features are extracted, it passes to layer 2 for more complex analysis, and so on, cascading through dozens of layers until it outputs a final classification. What a DDNN does is geographically split those layers.
Geographically split that.
Yeah, it physically places the first few shallow layers of the neural network on the end device, the next block of intermediate layers on the local edge workstation, and the final, most complex layers on the cloud.
Okay, I have an analogy for EEOI to make this concrete.
Let's hear it.
Think of this process like a bouncer at an exclusive high-security club. The club has multiple layers of security checks.
Okay, I'm with you.
So the end node, let's say it's a relatively cheap smart doorbell camera, is the very first bouncer at the velvet rope. Someone walks up and hands that bouncer a piece of cardboard with "I am 21" written on it in green crayon.
Nice.
The bouncer looks at it, immediately knows it's fake, and kicks them out. They do not need to call the manager to verify it. That is an early exit of inference.
That's a perfect analogy.
The low-level classifier, the first few layers of the neural network running locally on the doorbell, was mathematically confident enough to make the decision locally, instantly saving bandwidth and time.
Exactly. If the data is obvious, extract the simple features and deal with it immediately at the edge.
But what if a guest hands the bouncer an ID that looks very real, but maybe the holographic overlay is slightly suspicious? The bouncer's simple checks aren't enough, so they pass the ID up to the head of security, the central workstation inside the building, for a closer look.
Right, so the workstation runs the data through the intermediate, more complex layers of the neural network.
And if the workstation still cannot achieve a high enough confidence threshold,
It finally passes it up to the absolute highest authority, the cloud server, for the final, most resource-intensive check. This early exit strategy ensures that only the truly tricky, ambiguous data ever gets sent up the chain.
so most things stay local.
Yes, the vast majority of simple, everyday classifications are handled instantly at the edge. The research notes that utilizing this method reduced the total data communication cost by a factor of more than 20 for a multi-camera data set.
A 20-fold reduction in network traffic just by letting the bouncers do their job.
That's incredible. But wait, hold on. This introduces a massive wrinkle.
What's that?
We know these AI networks are constantly learning and getting smarter over time, but if the whole point of this local architecture is privacy, how do they learn? I mean, if my smart camera gets better at recognizing my face, I absolutely do not want it sending raw pictures of my face to a central server to train the main AI model.
That is the exact paradox that federated learning was invented to solve.
Yeah.
Federated learning is the concept of training a global AI model without ever sharing private data.
Okay, so how is that possible?
It allows an AI to get smarter by learning from the experiences of millions of devices, while ensuring the raw data never leaves the physical device that captured it. How does that actually work in practice? The research outlines a four-step process. Can you walk us through the mechanics of federated learning?
Sure, let's use the facial recognition example. Step 1. Millions of end devices, everyone's smart cameras, download the exact same base model from a central server. Everyone starts with the identical baseline brain.
Okay, so the central server pushes the starting point down to the edge. What's step 2?
Step 2 happens entirely locally. Your camera observes your face over a week. Using its local compute power, it runs a training process, like gradient descent, using your local private images. It tweaks and adjusts its own local copy of the neural network to recognize you better.
So it's customizing itself to me.
Exactly. My camera does the same thing at my house with my face.
So we both have custom, slightly smarter models now, but the central server is still dumb.
Right. Which brings us to the crucial step 3. Your camera and my camera do not upload the photos of our faces to the central server. They upload only the new parameters.
The parameters.
They upload the mathematical weights, the numerical adjustments that the local training process generated.
Oh, so it's like sending the recipe improvements back to headquarters without having to mail them the actual cake you baked. You're just sending the math.
Precisely. You send a matrix of numbers representing what the model learned, completely decoupled from the data it learned it from.
That is so clever. And step 4.
Step 4. The central server takes all these millions of mathematical updates from all the cameras, aggregates them, often using complex averaging algorithms, and fuses them to create a new, smarter, global model.
And then pushes it back out.
Then it pushes that upgraded global model back down to everyone. The system learns globally, but the private data remains entirely local.
It's a brilliant mathematical workaround for privacy. Now,
Uh-huh.
all of this distributed computing, early exits, federated learning, it requires specific hardware.
Right. Absolutely.
A standard, cheap router with a basic CPU isn't going to cut it. The sources highlight some of the specialized hardware making this possible at the very edge of the network.
The transition in edge hardware over the last few years is remarkable. The research contrasts the traditional Raspberry Pi, which is a fantastic, versatile machine, but ultimately relies on a general-purpose processor with specialized gear designed specifically for the mathematics of AI.
They heavily feature the Google Coral Dev Board.
Yes, they do. The defining feature of the Coral board is that it includes an edge TPU, a tensor processing unit.
How does a TPU differ from the CPU in my laptop?
Well, a standard CPU is great at executing a wide variety of sequential instructions quickly, but neural networks don't need a wide variety of instructions.
What do they need?
They need to do millions of matrix multiplications simultaneously. An edge TPU is silicon designed from the ground up utilizing what's called a systolic array to do that specific mathematical operation incredibly fast.
So it's a specialist.
Exactly. The source notes that for running a specific computer vision model, the MobileNet V2, the Coral Dev Board, performs 31 times faster than a standard Raspberry Pi.
31 times faster. That is the difference between a security camera, video feeds stuttering and freezing, and real-time, instantaneous object recognition.
It's a huge difference. And the research also points to developments at an even smaller scale, looking at ARML, ML processors, and CMSIS-NN kernels.
What are those?
CMSIS-NN is a software library designed to maximize neural network performance on deeply embedded, highly resource-constrained ARM Cortex-M processors.
Okay, embedded processors, where do we find those?
We are talking about putting AI inference on microcontrollers that cost less than $2 and run for years on a coin cell battery. It pushes the brain all the way out to the absolute furthest, cheapest edge of the network.
Wow. So we have built a network that processes data locally, shares the computational load dynamically across these specialized TPU chips, and protects our privacy using the math of federated learning.
It's a robust system.
But how does this architecture actually manage the network resources? Like, how does it solve that bandwidth battle we talked about in the very beginning with the video call choking because of the game download?
That brings us to a critical evolution in networking software. Agentic AI and quality of experience, or QoE. We are moving from AI that just passively recognizes a voice command to AI that acts as an autonomous, active network administrator.
Let's go the concept up for a moment. From a single smart home to a large organization like a university campus or a massive enterprise office building.
Okay, good idea.
The sources introduce intent-based networking, or IBN. What is the fundamental shift happening here?
To understand the shift, you have to look at how networks were traditionally managed. In a traditional enterprise, if a network administrator wants to ensure video calls get priority over file downloads, they have to log into dozens or hundreds of individual routers and switches.
Manually.
Yes, they have to manually type out command line interface instructions for quality of service protocols, configure VLANs, and adjust routing tables.
That sounds miserable.
It is incredibly slow, it is strictly reactive, and because it relies on human typing, it is highly prone to configuration errors that can take down the whole network.
The text mentions Cisco DNA Center and Juniper Mist AI as prime examples of this new intent-based networking paradigm. How do they operate differently?
They are entirely policy-driven. Under IBN, the network administrator no longer types out routing protocols. They simply define the intent.
The intent, like a goal.
Exactly. They type in a high-level business objective, prioritize VoIP traffic for the sales team, or ensure high availability and low latency for critical financial databases.
They just state the goal in plain English.
Exactly. And the AI policy engine automatically translates that high-level human intent into the hundreds of specific OSPF routing protocols, VLAN configurations, and firewall security policies required.
And it pushes them out.
Yes, and pushes them out across the entire physical network instantly.
It goes right back to our restaurant kitchen analogy. The restaurant owner doesn't micromanage the line cooks. The owner says, I want a new vegan menu launched by Tuesday.
Exactly.
The executive chef AI figures out all the complex recipes, orders the specific ingredients, adjusts the prep stations, and trains the line cooks automatically.
Yes. And beyond just executing a one-time intent, these AI systems use machine learning for predictive capacity planning. They don't just react, they anticipate.
The university exam season example in the text is perfect for illustrating this.
Right. An ML algorithm in an IBN system continuously ingests and analyzes real-time telemetry, things like SNMP data, application usage stats, and NetFlow.
Just to clarify for you listening, NetFlow is basically the metadata of the network, right? It shows who is talking to who and how much data they are sending without looking at the actual contents of the packets.
Correct. It's the traffic pattern data. So the AI analyzes this historical data and learns the patterns. It knows that every December, during finals week, traffic on the library's Wi-Fi network spikes by 400%.
Because thousands of students are simultaneously streaming study videos and accessing massive research databases.
Right. So it doesn't wait for the library network to crash on Monday morning.
It fixes it ahead of time.
Yes, the AI preemptively allocates bandwidth. Over the weekend, it autonomously adjusts quality of service policies, ensuring that critical university testing systems maintain guaranteed bandwidth while seamlessly deprioritizing casual web browsing or social media traffic entirely without human intervention.
That is wild. And the research also delves into machine learning for traffic engineering using reinforcement learning, which to a layman sounds like training a dog, but for routing data packets.
The underlying concept is very similar, actually. Trial and error, but executed at millionths of a second. A reinforcement learning agent interacts continuously with the network environment.
So it's constantly testing things.
Yes, it tries different routing policies, dynamically adjusting path selections for protocols like OSPF or BGP, which determine the actual physical path data takes through the network.
And what happens when it gets it right?
If the AI makes a routing change that reduces congestion and lowers latency, the agent gets a mathematical reward. Over time, it continuously learns the absolute optimal routing paths, dynamically navigating around traffic jams as they form.
This evolution of AI in networking is beautifully categorized by MediaTek in their research on AI-driven Wi-Fi systems. They trace a distinct three-step evolution. It starts with traditional ML.
Traditional ML is highly specialized but rigid. It uses manually engineered features to solve one specific narrow problem, like classifying what type of radio interference is hitting a Wi-Fi channel.
Okay.
It's useful, but it lacks broader context.
Then the next phase they outline is generative AI.
Generative AI brings in natural language processing and broad context. Instead looking at raw graphs of packet loss, an IT admin can type, "Why are users on floor 3 experiencing slow video calls this morning?"
And it can actually answer that.
Yes, the GenAI correlates the logs across multiple systems and provides a plain English diagnosis. It acts as a brilliant technical advisor.
But the holy grail, the third phase the sources point to, is agentic AI.
Agentic AI shifts the system from being just a passive advisor to being an autonomous, proactive operator. It utilizes what MediaTek defines as the closed-loop intelligence paradigm.
Intent, execution, and feedback. Let's walk through that loop mechanically.
The intent is defined by the user, for example, optimize video conferencing quality for this meeting.
Okay.
The agentic AI reasoning engine decomposes that high-level intent into execution. It figures out the specific API calls required to tune QoS parameters or switch Wi-Fi channels, and it actually applies them to the physical hardware.
To accomplish that execution, the research mentions the Model Context Protocol, or MCP. I want to unpack this because it sounds like we are giving the AI a physical toolbox.
That's precisely what it is. MCP is an architecture that allows an AI reasoning engine to use specific, structured APIs as tools. It bridges the gap between the AI's internal reasoning and external action.
So it can actually touch things.
Right. It gives the AI the ability to reach out into the physical world, observe the current network state, execute the configuration changes via APIs, and then read the new telemetry data to see what happened.
Which leads directly to the third part of the closed loop, feedback.
Crucially, after the agentic AI executes a change using its MCP tools, it doesn't just assume it worked. It reads the fresh telemetry to validate the outcome against the original intent.
Did the latency actually decrease? Did the jitter on the video call improve?
Exactly.
Okay, wait, hold on. You're saying we should just let an AI autonomously rewrite enterprise network protocols on the fly? What if it gets it horribly wrong?
That's a fair concern.
I mean, what if the AI's logic dictates that the most efficient way to optimize bandwidth for the sales team is to accidentally throttle the CEO's keynote speech because it classified it as non-essential video traffic? Giving an AI the keys to the castle sounds terrifying.
That is the exact nightmare scenario that keeps network administrators awake at night. And that is exactly why the feedback portion of the closed-loop system is the most critical safeguard.
How does the feedback stop the nightmare?
The AI is accountable to the real-time data. If the telemetry data shows that the change did not achieve the intent, if latency spiked, or if a critical connection dropped, the agentic AI is programmed to autonomously roll back the configuration to the previous known good state in milliseconds.
Oh, so it just undoes the mistake immediately.
Exactly, and then it tries a different mathematical approach.
Yeah.
It verifies and it corrects itself constantly.
It's a self-correcting engine.
Yeah.
And this ability to detect problems and fix them autonomously isn't just about making sure a Zoom call doesn't lag.
No, it's way bigger than that.
In the modern threat landscape, it is fundamentally about survival. And that leads us to the ultimate application of this entire architecture: security, digital twins, and the self-healing network.
Because if an agentic AI has the granular visibility to detect a bandwidth drop in milliseconds, it has the visibility to detect a malicious intrusion just as fast.
Let's talk about DIoT. DIAT with an umlaut over the I. It stands for Federated Self-Learning Anomaly Detection System for IoT.
Yeah.
Why did the researchers feel the need to build an entirely new detection system specifically for IoT security? Why couldn't they just use existing enterprise firewalls?
Because IoT devices like smart plugs, connected fridges, cheap cameras are notoriously vulnerable and behave very differently than laptops. The research highlights the rush-to-market mentality in the IoT industry.
Right. Everyone wants to make a smart toaster.
Yeah, manufacturers are pumping out these cheap connected devices as fast as possible, and rigorous security architecture is often completely ignored to save costs. Consequently, there is an entire category of malware specifically designed to infect these weak devices and conscript them into massive botnets.
So why do traditional network security tools fail to catch them?
Traditional anomaly detection often looks for massive volumetric spikes in traffic. If a server suddenly starts downloading terabytes of data, alarms go off.
Makes sense.
But a smart thermostat doesn't generate a lot of traffic. It sends tiny, infrequent packets of temperature data. A subtle, low and slow attack can easily hide in that low volume.
I see.
Secondly, traditional systems attempt to build one massive, generalized model of what normal network traffic looks like for an entire organization. But a smart fridge communicates completely differently than a Wi-Fi security camera or a printer.
Right. They speak different languages.
Exactly. And one broad, generalized model applied to everything generates a paralyzing number of false alarms.
If the security alarm goes off every time the smart fridge orders milk, the IT team is just going to mute the alarm.
Exactly. Alert fatigue is a massive vulnerability. So DIoT takes a radically different, highly granular approach. Instead of one massive model, it utilizes device-type specific model.
Okay, so a model just for the fridge.
Right. It profiles and learns the exact normal behavioral signature of just a specific model of smart plug, or just a specific brand of camera.
The methodology they outline here is fascinating. The text says it extracts 7 characteristics from the raw network packets. Things like the protocol used, the port number, the packet size. And then it maps those 7 characteristics to symbols.
It essentially translates the raw network traffic into a unique alphabet.
It creates a language out of the data flow. And then it feeds that continuous sequence of symbols into a GRU, a gated recurrent unit neural network.
Right.
How does a GRU work in this context?
A GRU is a specific type of recurrent neural network that is exceptionally good at analyzing sequences of data over time because it has internal memory mechanisms called update and reset gates.
So it remembers the past.
Exactly.
Right.
It doesn't just look at one packet in isolation. It looks at the sequence and asks, does this packet logically follow the previous packet? It learns the specific grammatical language of that one IoT device.
Oh, that's smart.
If the smart plug suddenly starts speaking a different language, if the sequence of packets deviates from the learned normal behavior, the GRU instantly flags it as an anomaly.
And the success rate they achieved in the study with this method is absolutely stunning. They tested DIoT against the infamous Mirai malware, which is the botnet that took down massive chunks of the internet a few years ago by hijacking millions of IoT devices.
The results are the definition of robust. The system detected 95.6% of the Mirai attacks.
But the speed is what truly shocked me. It detected the infections in an average of just 257 milliseconds, a quarter of a second.
Yes. The infection is identified and isolated before it can spread laterally across the network, and perhaps most importantly for practical, real-world application. When evaluated in a live smart home deployment, it achieved a 0% false positive rate.
Zero false alarms,
Zero.
which is the holy grail for security.
Yeah.
It acts as an autonomous immune system that isolates the infection without annoying the user.
Absolutely.
But if we scale this autonomous management and security up to a massive enterprise network, we run into a different logistical nightmare. Before an agentic AI pushes a major routing update or a strict new security firewall patch to thousands of nodes across a campus, how do you know it won't accidentally break everything?
You don't.
Right. You can't just test it live and hope the rollback works fast enough.
No, you can't risk bringing down a hospital network or a financial trading floor to test a patch. And that is where digital twin networks become essential.
Digital twins. I've heard this term.
A digital twin is a virtual, highly accurate, real-time replica of the entire physical network infrastructure.
How does a virtual model stay accurate to the physical reality?
By constantly ingesting the live telemetry data from all the physical network devices we talked about earlier, the net flow, the SNMP, the latency metrics, it builds a mathematical graph model that precisely mimics the current operational state of the entire infrastructure.
And the purpose of building this massive virtual replica is what the text calls AI-assisted what-if analysis.
Right. Let's say an enterprise IT team wants to add 50 new database servers, or they want to fundamentally change a core routing protocol, or deploy a draconian new security policy.
They test it on the twin first.
Instead of pushing it to the live physical network and holding their breath, they deploy the changes to the digital twin. The AI simulates the traffic flows, predicts the latency impacts, and highlights any security gaps or bottlenecks that would mathematically occur under those new conditions.
It's an ultra-realistic sandbox. If the digital twin crashes because of the new policy, nobody loses money, no critical calls drop.
Yeah, exactly.
You tweak the policy in the virtual environment until the twin is stable, and only then do you permit the agentic AI to deploy it to the physical world.
It drastically reduces operational risk. And when you combine all of these advanced elements we've discussed today, the local intent recognition, the vertically distributed compute, the privacy of federated learning, the granular anomaly detection of DIoT, and the safety of digital twins,
You arrive at the ultimate architectural goal outlined by Ashish Anand: self-healing infrastructure.
exactly.
Ashish Anand provides a brilliant 5-component framework that ties this entire deep dive together. Let's walk through it as a unified automated process.
Let's do it.
Let's say a critical fiber optic link gets physically severed outside a corporate office by a construction crew. Component 1, monitoring.
The network is continuously ingesting telemetry, logs, and metrics from every node and switch. It is always watching the baseline state.
Component 2, anomaly detection.
The AI models operating at the edge instantly spot a massive mathematical deviation from normal behavior. They detect a sudden 100% packet loss and a huge latency spike on that specific fiber route.
Component 3, Intent correlation.
The AI reasoning engine checks this physical anomaly against the high-level business policies. It realizes, wait, this dropped link breaks the SLA, the service level agreement, for our crucial video conferencing traffic. We are no longer meeting the human intent.
Component 4. Autonomous remediation.
In milliseconds, before a human network engineer even receives the alert on their phone, the agentic AI automatically calculates an alternative path, adjusts the BGP routing protocols using its MCP tools, and reroutes the traffic to a backup cellular or satellite connection, seamlessly restoring the video calls.
Wow. And finally, component 5. The learning loop.
The system feeds the telemetry data from this failure and recovery event back into its models. It learns how the network reacted to the specific failover protocol, refining its future predictions and responses. The network healed itself, and it got smarter in the process.
So this brings up an incredibly important question, one that's highly relevant to a lot of people working in tech right now. If the network is entirely self-healing, adapting, and defending itself in milliseconds, using federated learning, agentic AI, and digital twins, are human network engineers going to be out of a job?
The common fear. Yeah.
Are we automating away the IT department?
It's a very valid anxiety, but the sources we are looking at, particularly the insights from institutions like Networkers Home, suggest the job doesn't disappear. It evolves significantly and necessarily.
So the days of manually typing out command line interface configurations device by device are over.
The data strongly points to that, yes. Network engineers will shift from being the manual laborers of the network to being the high-level architects.
What skills will they need?
They will require an entirely new skill set. Proficiency in Python, a deep understanding of how to integrate APIs, and a solid grasp of machine learning concepts will be mandatory.
So they have to understand the AI.
Yes. They will be the ones designing the digital twins, defining the high-level intents, and crafting the business policies that guide the agentic AI. They will manage the intelligence rather than manually managing the cables.
They become the executive chefs designing the complex menus and managing the AI sous chefs, rather than being the line cooks manually chopping the onions.
That's the reality. The scale and complexity of modern infrastructure, billions of IoT devices, microsecond latency requirements, is growing so fast that human manual management is simply no longer mathematically viable.
It's just too big for humans.
Right. The AI isn't replacing the engineer. The AI is the required tool for the engineer to manage the new scale of connectivity.
Okay, let's bring this all together. We have covered a massive amount of technical ground today. We started with the very real, visceral frustrations of centralized cloud architecture.
Right, the constant battles for bandwidth, the severe privacy leaks, and the sheer economic burden of sending billions of raw data points to remote servers.
And we explored the architectural solution, bringing the brain back into the building. Architecting a system with one powerful central workstation, managing multiple local nodes, utilizing microservices to handle complex tasks concurrently without introducing lag.
We saw how that local workstation doesn't have to shoulder the burden alone, but actively distributes the compute load dynamically across the network.
Utilizing early exits and federated learning to get smarter and faster without ever sacrificing privacy. We looked at how agentic AI can take our high-level intent and autonomously manage our quality of experience.
And finally, we saw how these local AI ecosystems act as an autonomous immune system, detecting anomalies like the Mirai malware in fractions of a second and healing the network infrastructure without human intervention.
Whether you are a homeowner trying to set up a smart house that truly respects your privacy and doesn't freeze your Zoom calls, an IT administrator managing a school building full of connected tablets, or an enterprise architect designing a secure global network, understanding this edge compute revolution gives you the blueprint for the future of connectivity.
It really does. The cloud isn't going away, but it is no longer the center of our digital universe.
The intelligence is moving back to us.
It is a profound, necessary redistribution of digital power and intelligence back to the local edge.
Which leaves me with a final, slightly mind-expanding concept to mull over. We've talked entirely about these systems working within a single building or a single organization. But if our individual homes, classrooms, and offices are becoming these highly autonomous, self-contained, self-healing AI ecosystems, what happens in the near future when your home's AI workstation decides to seamlessly negotiate bandwidth and compute resources with your neighbor's home AI workstation?
Oh, wow. That is the logical, albeit wild, next step. Device-to-device meshes naturally evolving into home-to-home, building-to-building meshes.
We might not just be looking at the end of centralized cloud computing. If these local workstations start collaborating peer-to-peer across neighborhoods, well, we might be looking at the birth of a decentralized, organic, global superorganism built entirely out of our living rooms. Something to think about the next time your video call freezes.